If you lived in Kuala Lumpur a couple of decades ago, you knew the drill. A heavy monsoon rain meant one thing: destructive flash floods that could swallow your car whole. On top of the water damage, the city faced a daily, grinding struggle. Severe traffic congestion choked the roads, costing residents massive amounts of time, lost productivity, and mental stress. Today, that intense combination of underwater parking lots and gridlocked roads is incredibly rare in the city center. A massive intervention solved the problem. The answer is hidden right under the streets. This is the Smart Tunnel, a colossal megastructure built as a dual-purpose shield for the city above. This massive concrete tube serves a highly specific purpose. It is physical proof of a powerful engineering strategy in action: sustainability. When you hear the word sustainability, you might immediately picture recycling bins, solar panels, or planting trees. This chart outlines the actual definition used in civil engineering. Notice how environmental protection is balanced equally with social sustainability on the top right and economic sustainability on the middle right. Let's apply that to the Smart Tunnel. On the environmental side, the tunnel is built to handle the intense reality of tropical storms. During heavy rain emergencies, it can swallow up 5 million cubic meters of floodwater, keeping the city perfectly dry. Then there is the social side. On dry days, the tunnel converts into a highway. This cuts a stressful hour-long commute down to a quick drive, directly improving the daily mental health and well-being of thousands of people. Finally, the economic side. Building a megastructure like this requires a massive upfront investment. However, by preventing total gridlock and keeping floodwaters out of downtown businesses, it saves the country billions of ringgit in avoided property damage over its lifespan. True sustainable engineering solves human, financial, and environmental crises all at exactly the same time. So how do planners actually guarantee that every new highway or hospital hits all three of those targets? They rely on strict legal frameworks and points-based grading systems. These rules force contractors to measure and reduce their impact before they ever break ground. The first tool is the EIA, or Environmental Impact Assessment. Think of it as a mandatory X-ray of the project. If a road threatens a crucial forest, the EIA forces engineers to redraw the map and curve around the danger zone to avoid ecological damage. You can see this in action with Malaysia's East Coast Rail Link. Because of the EIA, engineers built these massive elevated viaducts. This allows local wildlife to safely migrate underneath the tracks, keeping the ecosystem completely intact. Once the actual digging and moving of soil begins on a site, crews must follow an ESCP, the Erosion and Sediment Control Plan. This rule forces contractors to build traps that catch mud, ensuring nearby rivers don't choke and flood during heavy rain. This table shows tools used to measure the long-term impact of a building. Notice the rows for GBI and MyCrest. These act as energy and carbon calculators, grading a building's design to ensure it stays cheap to power for the next 50 years. These acronyms represent the operating system of modern construction. They keep a nation's infrastructure alive, safe, and profitable. This brings us to a major shift in how civil engineering operates. The old philosophy of building as fast and as cheap as possible is obsolete. The new standard is to build smart and build lasting. Traditional construction often involves pouring concrete on site in the dirt, a messy process that generates a huge volume of timber and material waste. Modern engineering requires precision. That precision is found in the Industrialized Building System, or IBS.